So it's very nice to be back. So what I'd like to talk about today is some work that we've been doing over the last few years, studying really the last year or so, last year to decade in the lives of massive stars, and how that connects to some of the different phenomena shown here at the bottom of this image, convection, luminous supernovae, and anybody guess what the middle one is? Except Jeremy. Yeah, that's right. So this is flow over an island. So flow over topography in the Earth's atmosphere excites what are called internal gravity waves, which actually propagate up through the atmosphere and mix. This is one of those subgrid things in global climate models, is mixing introduced by internal gravity waves redistributing momentum, in this case kind of shear-wise momentum in the Earth's atmosphere. And this will be related to some of what we'll end up talking about in the cores of massive stars. So I want to start just by providing a little bit of context. So some of the observations that I think motivate thinking that something unusual is happening in the latest stages of massive stellar evolution. So that in the last few years of stellar evolution, there are some very unusual phenomena distinct from what happened in the earlier tens of millions of years of stellar evolution for massive stars. Then I'll kind of review very briefly some of the physics of massive stellar evolution, and then focus in particular on the role of what is really non-local transport of energy and angular momentum in stellar interiors by waves. So this is something that's been considered in the context of the sun, for example. The interior of the sun is in solid body rotation. There's two major ideas for why that might be. One is angular momentum transport by waves, and the other is large-scale magnetic stresses. But for reasons that you'll see, this redistribution of energy and angular momentum by waves in the cores of massive stars at the end of their lives is particularly important, in fact, even much more important than it is in the case of the sun. So just to start providing a little bit of context for this, we know a kind of dizzying variety of core collapse supernovae. I'm going to focus on one in particular that constitutes about 10% of core collapse supernovae, and these are known as type 2N supernovae. The N stands for narrow lines. And what these are supernovae where the emission we see is not powered by radioactive decay of nickel, but rather it's powered by the supernova shock running into surrounding material relatively close to the massive star. And the kinetic energy of the shock as you sweep up this nearby material, the material gets shock heated to high temperatures and it radiates away its energy efficiently. So this is in some ways analogous to a supernova remnant where you have a radiative supernova remnant. The supernova shock goes into the interstellar medium, radiates away its energy. The principal difference is this is happening not on the scales of parsecs or tens of parsecs like in supernova remnants, but it's on scales of hundreds of AU, so really on scales of the stellar system. So it's circumstellar interaction rather than the interstellar medium. And what's special about this radius, just to give you a sense of the physics, is that if you do a simple estimate and you ask the question, if the supernova shock runs into material, what is the ratio of the diffusion time of photons through the material that's been shock heated relative to the expansion time of the material that's also been accelerated to some high velocity? So this is kind of a comparison of the efficiency of radiation versus the efficiency of adiabatic losses. It's adiabatic losses that normally make supernovae rather inefficient at producing photons. Most of the kinetic energy of the shocked stellar envelope, that energy, that thermal energy of the shocked stellar envelope is lost due to adiabatic expansion rather than being radiated away. But if material is at the right place when it's shock heated, and the right place is where the diffusion time is comparable to the expansion time, then you very efficiently convert shocked energy into radiation. And that's the case at about 100 AU. That's the location where the diffusion time is comparable to the expansion time. And so you convert lots of shock kinetic energy into radiation. And this is very large compared to stellar radius. This is 10 to the 4 or more solar radii. So this is large even compared to red giants. And so what that means is that what this is really probing is not so much the stellar photosphere, but rather it's probing material that was lost just prior to the supernovae. Material moving at a few hundred or 1,000 kilometers a second in a wind ends up at 100 or 1,000 astronomical units after a few years. And so these type 2n supernovae that show evidence for emission powered by interaction with ambient gas are really probing the kind of structure and dynamics of the star in the few years prior to core collapse via the mass that was ejected just prior to core collapse. So just to give you a feel, this shows an example of a spectrum. This is the H-alpha line in one particular type 2n supernovae. The name type 2n, the n stands for narrow, because one of the things you see in these supernovae, you see in addition to the standard broad supernova lines of 10,000 or 5,000 kilometers a second, you also see relatively narrow lines of 500 or 300 or 1,000 kilometers a second, which are interpreted as being photoionized gas in the wind. So you see simultaneously in the spectra of these type 2n supernovae, you see indications of the wind spectroscopically, and you see the broad supernova lines. And so just to give you a feel of how you infer some of the characteristics of the wind, so the width of the narrow line gives you information about the speed of the wind. And then if you have a radiative shock, the luminosity of the radiative shock is basically that all of the swept up kinetic energy, so the mass you sweep up times v squared of the shock, so that's the kinetic energy swept up, in the limit of arbitrarily short cooling times, you radiate away the swept up kinetic energy on a dynamical time. The rate limiting step is sweeping stuff up, not radiating the thermal energy away. And so the luminosity scales something like the density of the wind times the speed cubed of the shock going into the wind. And so what this means is if you can measure both the speed of the wind and the speed of the shock, and you can measure the luminosity produced by this interaction between the shock and the wind, you have a way of measuring the density of the wind, the speed of the wind, and hence the mass loss rate prior to core collapse. So it comes out right. So there's an efficiency factor which is calibrated based on models of shock. So actually, an appreciable amount of the energy comes out in line emission. That does depend on exactly how high the optical depths are. If you have sufficiently high optical depths, you can actually thermalize a lot of the lines and get more continuum emission. So there's actually different regimes you can be in. So yes, there is some calibration here from models of shock excitation of lines. So this just summarizes some of the inferences. This shows mass loss rate as a function of wind speed from a set of these type 2n supernovae, which were analyzed. And just to give you a feel for the types of mass loss rates we're talking about, they range from maybe 10 to minus 3 solar masses a year up to about a solar mass per year with wind speeds of a few hundred to 1,000 kilometers a second. Right. So, in some cases, we have a constraint on how long it lasted, which is because as the supernova shock goes out, eventually the signs of circumstellar interaction go away. There's also a pretty good upper limit on how long it lasted by taking m dot times time to be less than 30 solar masses. So this is probably decades. At the lower m dot, it could be centuries, something like that. That's right. So this is
energy compares how with 10 to 51 ergs.
So the total energy is less than 10 to the 51 ergs, but it can be 10 to the 49, 10 to the, a few times 10 to the 49 ergs in some cases. So it can be an interesting amount of energy. So they're actually, so I didn't go into that. There are in some cases also spectroscopic diagnostics. There are at least constraints on the densities. You also sometimes see the wind. There's some evidence, yes, for clumping in the winds. You do see evidence sometimes for broader wings, which are due to Thomson scatterings. You get additional radiative transfer effects due to multiple scatterings producing broad wings as well. So there's a lot of additional observational diagnostics that I'm not going into here. So this m dot is the m dot inferred via the supernovae running into stuff. So this is not telling you about mass that was lost 1,000 years before, which is much further away. So this is only some statement about mass loss really in the last decade or so of stellar evolution. So the most extreme version of this phenomena was discovered really only in the last decade or so. These are called superluminous supernovae. This gives you an idea. So this is just a bunch of different supernovae. This shows luminosity as a function of time. So just to kind of orient you, the blue here are type 1a supernovae. These systems up here are examples of what are called these superluminous supernovae. So these are systems where the radiated energy approaches 10 to the 51 Earths. So this is a case where, unlike in normal supernovae, where the radiated energy is maybe 1% of the shock energy, 10 to 49 Earths, in rare cases, the total bolometric luminosity kind of the supernova approaches the kinetic energy of the shock. And there's actually, as always, there's type 1 and type 2 supernovae. So one class of these, you see these narrow lines indicative of a slower wind. And so one class of these is believed to be powered by circumstellar interaction, where the supernova shock is running into a particularly large amount of material. And so you shock and actually decelerate substantially the supernova shock in this vicinity of 100 or 1,000 AU. So you tap into a large fraction of the kinetic energy to power the supernovae emission.
You have an independent measurement of the kinetic.
You have,
Can it be 10 to the 52?
so it's, yeah, it is possible actually that you have 10 to the 52. I mean, there's some independent constraints at later times. You know, you try to measure the ejecta mass, you have velocity information. So I think the total kinetic energies are actually uncertain, so it is possible these are somewhat energetic. And some of these actually do go up in terms of radiated photon energy to 3 times 10 to the 51. I mean, so they get quite substantial.
Do you ever think some of these systems early enough to give narrow lines? You push the numbers, it should be true.
So I'm not, yeah, that's a good question. I'm not sure is the honest answer. I don't, off the top of my head, I don't know of a case, but I'm actually bad at remembering all of the different supernovae that have been discovered, and so I'm not 100% certain whether one has been caught early. So the other thing that's started to be discovered really in the last 5 years as a result of dedicated time domain surveys is that we're actually seeing just photometrically in monitoring stars prior to their explosion. So you take, this is from the Palomar Transient Factory, you take an object which was discovered as a supernovae in PTF, you go back to its location prior to the supernovae, and what you see is that actually it's not just non-detections, there's kind of a bump in the light curve prior to the supernova rise, and there's something like 10 or so of these events that have been discovered now where in the period of a few years to a few months prior to the nominal supernovae explosion, you see a dramatic increase in the luminosity at the same position. And the luminosities, to basically, because these are the only ones we can detect for most of these systems, the luminosities are well above the Eddington luminosity in these outbursts. And this is interpreted to be basically the ejection of material prior to the core collapse supernovae that you then see via interaction when the supernovae runs into. So that's the interpretation. The observational phenomena is just now that we have densely sampled light curves for many supernovae, you can go prior to the supernovae, and you can actually see that there's all kinds of interesting activity in a set of massive stars prior to exploding. So to a sense of the statistical implication, so it's tricky because the statistics from surveys like and pan-stars are not great. There's all kinds of complicated selection effects that they largely choose to ignore. So they report interesting events, but they haven't done a careful statistical analysis. So this is a very rough statistical analysis of what the incidence of these large mass loss rates actually tells us. So the way to think about this is what we're seeing is that stars are ejecting an interesting amount of mass, a fractional change in mass delta m over m, which might be something like 10 to the minus 3, 10 to the minus 4, 10 to the minus 2. Right, that's a tenth of a solar mass a year, a hundredth of a solar mass a year, up to a solar mass a year. And they're doing it in a fraction of the star's lifetime that is extraordinarily small. A massive star's lifetime is tens of millions of years. And so the fraction of the lifetime that this mass is ejected is 10 to the minus 6, 10 to the minus 7, something like that. And so what you might expect is that if the mass loss were completely uncorrelated with when in stellar evolution the star was, if it didn't know anything about the star being about to explode, then you might expect that the fraction of systems where the mass loss happened very near the end of the life of the massive star would be something like the ratio of these numbers, and so it would be a very small number, the ratio of these numbers. In fact, you see evidence for very large mass loss rates in a large fraction of core collapse supernovae, something like 10% of core collapse supernovae. The most extreme cases, these superluminous supernovae, are rare, but that's the kind of tail end of the luminosity function. And so I think this argues strongly that there's something physically connected to the late stages of massive stellar evolution that is enhancing significantly the probability of very large mass loss rates from stars. And so I think this argues that we should look to the physics of late stages of massive stellar evolution to try to understand what's going on. And so what I want to do is just briefly remind you about some of the basic physics of stellar evolution, what's different about massive stars than low mass stars, and that'll point towards the physics that I'll try to convince you is particularly important for understanding this mass loss. So normally when we think about stellar evolution, we think about energy balance in stars is basically that energy generation by fusion equals the energy taken out of the star by some combination of convection and photon diffusion. And that's true on the main sequence and throughout low mass stellar evolution, but it's not true in late stages of massive stellar evolution. By the time you get to stars that are fusing carbon or heavier elements, so carbon, oxygen, neon, silicon fusion up to forming the iron core, at that point, the temperatures required to fuse carbon are high enough, approaching 1 billion degrees Kelvin, that thermal neutrino cooling starts to dominate over photon cooling. And so the rough zeroth order energy balance in the cores of massive stars from carbon fusion on is that energy generation by fusion balances energy neutrino losses. And that is, in general, much larger, actually, than the energy that leaves the star by photons. The photon luminosity is of order the Eddington luminosity, but the fusion luminosity in the core of a massive star at the end of its life is actually much larger than the Eddington luminosity due to photons, the photon Eddington luminosity. It's, of course, much less than the neutrino Eddington luminosity. But this really is the energy balance then in the cores of massive stars. And so this just kind of shows this quantitatively. So the dark solid line here is the neutrino cooling curve. This is thermal neutrino emission by neutrino bremsstrahlung, pair production, a variety of different processes. So this is energy per second per gram generated by neutrinos, and then the thinner lines are energy generation by carbon, neon, oxygen, and silicon fusion. And each of these yellow circles is basically a quasi-steady state phase analogous to the main sequence. This is where carbon fusion bounces, neutrino losses, neon fusion bounces, neutrino losses, etc. And so one of the other things you'll notice is that the strong variation of neutrino cooling with temperature leads to a huge change in the amount of energy generation and the amount of energy loss by neutrinos in order to be in thermal equilibrium. So oxygen fusion generates a luminosity which is 10 to the 4 times larger than carbon fusion in the cores of massive stars. Silicon fusion is a factor of 100 yet larger. What this means is that massive stars at the end of their life go through their fuel incredibly quickly because the fusion rates are 10 to the 4, 10 to the 5, 10 to the 6 times higher than they were in earlier stages of stellar evolution. So, for example, a 25 solar mass star that has a main sequence lifetime of, say, something like 10 million years, so that's carbon fusion in such a star takes about 1,000 years. The fusion luminosity at that point is a little bit bigger than the photon luminosity, maybe 10 times. So it's about 1 million times solar. Neon fusion, so now we've moved up in our thermal equilibrium. Neon fusion takes only a year. The fusion luminosity is about 1 billion times the luminosity of the sun. Oxygen fusion also takes about a year. Silicon fusion takes about a day. And the fusion luminosity at the end of the life of the star is about 1 trillion times the luminosity of the sun. And again, the reason for this, it's basically, to 0th order, it's the same amount of fuel that you're going through. It's about a solar mass of fuel. On the main sequence, it's hydrogen. In later stages of stellar evolution, it's whatever's listed here. What's accelerating stellar evolution is the neutrino cooling sensitivity on temperature, which forces you to go to these very rapid energy generation rates and hence go through the fuel very quickly. Now, the standard story, the textbook story for massive stellar evolution is that while this is happening in the core of the star, and fusion is generating 1 billion times the luminosity of the sun or 1 trillion times the luminosity of the sun, the standard story is that that essentially has no effect on the rest of the star. The neutrinos are optically thin. So yes, the core is generating this prodigious amount of energy, but that just leaves the star by neutrino emission, and it has no effect on the rest of the star. So this, the thermal time of the rest of the star is long, right? So it's exactly, and so that's part of the argument that the star can adjust because the thermal time of the envelope is much larger than the timescales listed here. And so the story is the envelope basically decouples from the core. That's the standard story in massive stellar evolution. There's all this neat stuff happening. You're burning through amazing amounts of fuel, 1 trillion L sun of fusion, but the envelope doesn't know anything about that. It's completely optically thin in neutrinos. The thermal time is very short. And so the envelope, the story is basically frozen while the core is doing all of this interesting dynamics. Well, it's still in thermal equilibrium because the energy generation by fusion bounces neutrino cooling. So hydrostatic equilibrium is no problem at this phase. I mean, it will be a day after this. It'll be a problem, but it's okay at this phase of stellar evolution. No, that comes out of the calculate, meaning the. So I would say if you solve the spherically symmetric time-dependent stellar structure equations, you do get that the photon luminosity doesn't know anything about what's going on in the core. That neutrinos carry away all of this energy. I would say it's still an assumption for reasons I'll get to, but in a standard spherically symmetric model, that is a result of calculation. That's why I emphasize time dependent. I mean, I think you don't need to assume. So I would say spherically symmetric is certainly a big assumption there, but it's not. I would say it's not really assuming that it's hydrostatic.
So if I just go and fire up Mesa, it will do all this.
Yes.
You haven't told us anything that's not in Mesa.
Yes, that's right. Okay. So the argument I would make is that the way to think about mass loss in late stages of stellar evolution is really, if you think not in terms of time, but in terms of energy released by fusion, then the late stage mass loss actually isn't all that surprising. You're going through this fuel very quickly, but you're actually just tapping into the energy available from fusion to power mass loss. You're definitely, well, you're changing the composition very quickly, yes. That does lead to all kinds of shells of different composition. It leads to semi-convection. I mean, it does affect the structure, yes. And whether, I would say that in particular, I'm not sure is well modeled in standard, spherically symmetric models. So my view is that really, this is the obvious energy source to think about for powering, unusual mass loss in late stages of stellar evolution. And the question then becomes, what is wrong about kind of standard spherically symmetric stellar evolution such that it can't tap into that energy source? And so there's a couple of different ideas that have been proposed. So one is there actually is in very, very massive stars, 120 solar masses or so, they undergo something that's called pulsational pair instability, where in the last decade or so you have a kind of runaway collapse, which generates a thermonuclear explosion of a shell, which unbinds some material. But this seems to be restricted to only the most very massive stars, is probably not relevant to the majority of mass loss that we're seeing associated with interaction in supernovae. The other idea that's been proposed is that we know from spherically symmetric stellar evolution that in lower mass stars, thermonuclear fusion can sometimes be unstable, as Martin Schwarzschild. Thin shell fusion, for instance, of helium on the asymptotic giant branch is unstable, and this is relevant for mass loss on the asymptotic giant branch. The problem is those mechanisms of generating unstable fusion get quenched when you're primarily supported by radiation pressure. And so at least spherically symmetrically, shell fusion is stable, but maybe when we do multidimensional calculations, Nathan Smith in particular has argued that it would be nice that if multidimensional simulations showed that fusion was actually unstable, because that would be useful for this kind of phenomenology. So that's a possibility. No mechanism has been identified because the mechanisms we understand for fusion being unstable actually don't work for massive stars. So the mechanism that I'll tell you about is some work that we started to do a few years ago, which is fundamentally related to the role of convection in the cores of these massive stars. So this is a diagram that stellar theorists like and nobody else really understands, that's meant to convey the internal structure of stars as a function of time. So what this is plotting, this is time, and this is enclosed mass. You can think of this as kind of a radial coordinate. It's a mass coordinate inside the star. This is the surface of the star. This is the interior. The only thing that's important here are the gray regions, which represent convection. So this is a star that on the main sequence had a convective core. Massive stars have convective cores on the main sequence. Later stages of stellar evolution, it's a red giant, so it has a convective envelope in later stages of stellar evolution. And the thing I want you to notice is that in late stages of stellar evolution, fusion in the core is associated with these convection zones, right? This is about a solar mass. So that's the core of the star, and you get shell fusion. And the basic physics of this is that in an average sense, fusion and neutrino cooling balance each other. But these are different functions of density and temperature, different physics that sets the dependence of fusion, energy generation, and neutrino cooling on density and temperature. And so they can't balance each other everywhere point by point. So averaged over the inner few solar masses, fusion energy generation balances neutrino cooling, but it doesn't balance kind of point by point in the star. And what that means is that there's a mismatch between energy generation by fusion, energy loss by neutrinos. And if you try to fuse energy at a rate that's much larger than the Eddington luminosity, you generate convection. You're dumping a bunch of energy into the core of the star by fusion. It generates convection. And in the standard story of massive stellar evolution, what convection does is it basically takes fusion energy from the inside, where fusion energy generation is a little bit bigger than neutrino cooling, and it just brings it out a little bit in mass or radius to where neutrino cooling is a little bit bigger than fusion energy generation. So convection moves energy around in the standard story so that neutrino cooling and fusion balance each other integrated over the core of the star.
Is the temperature of the center of the star very high?
Yes. It's between 1 and 4 billion degrees at this time.
But it's not high dynamically compared to the structure of the star?
Well, it's in hydrostatic equilibrium, so I would say the temperature is the virial temperature. I mean, pressure balances gravity. So it's hot. It is of order the dynamical, the pressure due to gas and radiation is of order of gravity. Okay. So the picture then is that in the late stages of massive stellar evolution, we have this incredibly vigorous convection that's moving energy around. And the standard story is it's just moving energy around so that neutrinos can carry that energy away. And what you have then is you have multiple convection zones bordered by stably stratified regions. And this is a numerical simulation done by my student Daniel Lequanet that shows you a convection zone. These are entropy fluctuations in a convection zone. And then these are actually vorticity fluctuations in a stably stratified layer. So what this is, there's a transition here between a convection zone and a stably stratified layer. This is undergoing convection. Convection hits the boundary, the transition zone between convection and radiation, and some of the energy from convection gets dumped into waves, which then propagate out into the stably stratified region. And you're seeing those waves in the velocity field here in the stably stratified region.
How large are the convective velocities?
They're actually, it's so dense. So you might think if convection is carrying around an energy that's huge compared to the Eddington luminosity, you might think the velocities are big. It's still quite subsonic, 10 to the minus 2, 10 to the minus 2.5, something like that. And it's because the densities are enormous. So rho v cubed isn't actually, v doesn't need to be that large to carry the energy. So we actually have a okay statistical understanding of the properties of waves excited by convection. Waves excite both, convection, excites both sound waves and internal gravity waves. Internal gravity waves for subsonic convection carry the majority of the energy away because convection is basically pseudo-incompressible, so it couples better to the pseudo-incompressible internal gravity waves than sound waves. And the numbers to remember are that roughly the energy flux in convectively excited waves is roughly the convective Mach number times the energy carried by convection. And the frequency of those waves is basically the convective turnover frequency. And this we know from analytic theory and from numerical experiments. And to be fair, I think these numbers are all uncertain at the factor of 3 level.
G waves don't steepen as they go out.
These waves don't steepen very much as they go out for various reasons that I can come back to. So here's the picture then, the more nuanced picture of the core of a massive star near the end of its life. very vigorous convection driving a huge amount of energy into outgoing waves. And the question then is, what happens to those waves? Do they damp before they go anywhere? Do they reflect and come back in which case they're not all that interesting? Or do they actually propagate out into the stellar envelope, in which case they can non-locally redistribute a huge amount of energy? And so we've tried to do this calculation. I think the most uncertain part of the calculation is what is the exact wavelength, the characteristic wavelength of the waves that are excited by convection. If the waves excited by convection have wavelengths comparable to the scale height in the convection zone, which is what we think from analytics and numerical experiments is the case, then in many cases, what can happen is the waves don't get reflected and come back in, but they actually tunnel out through kind of a barrier that exists in the stellar atmosphere, and they become outgoing sound waves in the stellar envelope. So waves that are excited, supported primarily by buoyancy, can in a different part of the star be supported primarily by pressure, and that's what actually happens in this case. So the waves transition from internal gravity waves to outgoing sound waves. As the waves travel out, they're actually very linear. This physics is all linear. The excitation is nonlinear, but the propagation is linear. This is a standard WKB tunneling calculation. The sound waves in the envelope are very linear. They don't shock. They propagate out until the photon diffusion time gets short enough that the waves damp by radiative diffusion, and then the energy that the waves are carrying gets thermalized. It gets dumped into the stellar envelope by radiative diffusion. So the situation then in this example of core oxygen fusion is that the fusion luminosity might be 10 to the 10 times the luminosity of the sun. The wave power, outgoing wave power, might be something like a percent or so of that. So 10 to the 7.5 times the luminosity of the sun, which is maybe 100 times the Eddington luminosity. If you want to think in terms of energy, the total fusion energy liberated fusing oxygen is about 10 to the 51 ergs. And the fraction of that energy that's tapped into by waves can be a few times 10 to the 48 ergs. The propagation time through the envelope is less than a year. It's a few months, depends on the exact model. It's mostly actually dominated by the propagation time as internal gravity waves, because the group speed of internal gravity waves is slow compared to that of sound waves.
So it's not much slower than the oxygen burning.
Correct. It's not much slower. That's correct. But it's less than the lifetime of the star until core collapse. It's less than or less than.
By a factor of 2?
By a factor of 10, I would say.
10?
A year, a month.
A year, a month.
Yeah.
You have this big phase in the last year. If I remember your diagram,
Yep.
there were several other periods of time where the star was convective.
Yeah, I'll come back to how this varies with different types of stars and time in just a second. Yes. Okay. So what happens then if you dump this much energy into the envelope of a star? I think you can probably guess. The answer is that you blow away the envelope. You can actually do real calculations of this. So this is an example done actually with the MESA stellar evolution code that Scott referred to. MESA now has the ability to solve the time-dependent equations of hydrodynamics. So you can actually study stellar winds with MESA, not just hydrostatic stellar evolution. So this is an example where I took a model of a massive star, I dumped in an energy at a rate motivated by these types of physical models, and I watched the response of the star. The envelope puffs out to become a red giant, but then actually you dump enough energy in that the envelope becomes unbound. This shows mass loss rate as a function of radius. This shows density profile as a function of radius at different times. You actually set up a steady state wind with a mass loss rate of about a third of solar mass per year. The nicest thing about this calculation is that it's actually all completely explicable analytically. So we actually have a nice analytic theory that describes the kinematics and mass loss rates for these types of very super Eddington winds. These wind models are relevant not just in this physical situation, but in other situations like common envelope evolution in binaries, Eta Carina, things like that. This is a spherically symmetric calculation. The assumption about how the energy was deposited is that I go into MESA and I add an if-then statement, meaning I put energy at roughly the physical location at roughly the rate that I think where it should damp from kind of my model of sound wave propagation. So it's phenomenological. It's kind of motivated by this, but it's not self-consistent in the sense that I just specify a location, I dump energy in. It's not kind of dynamically, self-consistently calculated where to put the energy in or anything like that. In the core of the star? Yeah, the convection, I mean, that's the kind of related to this question about the speeds. The convection is still quite efficient. So the entropy gradient is pretty small. That's right. And that's why the convective turnover time is actually long compared to the dynamical time. So Rodrigo took these ideas and instead of doing spherically symmetric simulations, did some three-dimensional simulations in Flash, which are exactly the same spirit, namely we go to a place in the stellar model where we think the energy should be deposited. We dump it in at the rate we think it should be deposited, and we watch what happens. So the units here are position in units of where the energy is deposited. So 1 is the heating location. This is actually a three-dimensional simulation. Most of the calculations we did are two-dimensional simulations. And what this shows you is the speed of the wind. What it will show you is the speed of the wind relative to the escape speed where the wind is launched at the heating location. And so what you see is initially kind of very vigorous convection as the structure readjusts. And then it actually settles into a steady state wind. In this case, the speed of the wind is a third or so of the escape speed at the location where the energy is deposited. And again, at least for me, what was particularly satisfying about this is that all of these wind properties we can understand using an analytic model of the wind. It's a version of the Parker wind. That's exactly right, with some differences because radiation pressure domination, but it's a version of the Parker wind, exactly.
How far were you from actually solving the calculating the convection?
Yeah, so I don't have plots of that here, but there have been simulations by Casey Meakin, Dave Arnett, Sean Couch that have focused just on the core of the star, and they see excitation of gravity waves with frequencies, wavelengths, and rough amplitudes consistent.
But can you
You can't, that's very hard. I mean, the stellar radius is quite big. Evolving the core month to follow the propagation of the waves all the way out is still challenging. What is the time scale? Yeah, so the units of time here are dimensionless, but in reality, this simulation is a year or so.
So it's like the same time scale.
No, because it's not the core of the star. It's just the envelope of the star.
Sure, no, I agree. So usually the problem is just if you just different length scales, so in principle there is no problem because you can do AMR, you can like make the same functional resolution. But if there is no time problem, why can't you do that?
So you have to, I mean, I'm not sure how you're envisioning doing this calculation. You have to model the convection in the core. Maybe if you use a model where you treat that using something like anelastic, where you don't do full hydrodynamics. Okay, I look forward to seeing your results on that. No, I mean, I think this is clearly the direction this is going, is to do more realistic multidimensional calculations. I do think it's still a challenge to do fully the core and the envelope at the same time. There isn't really a gamma. I mean, these are gamma equals 4/3 because it's radiation dominated. But what matters is that there's a lot of heating. And so you have to solve the energy equation with heating. But it is a version of the Parker model with a physically motivated source of heat. Yeah, so here it's slightly more sophisticated than just putting a gamma in. So just in terms of mass loss, with this energy budget, if you eject material moving at about 300 kilometers a second, the total mass that could be unbound is of order of solar mass. In many cases, depending on exactly where the energy is deposited and some other properties of the models, a lot of the energy actually goes into simply unbinding material from the potential well. It doesn't go into asymptotic kinetic energy. So this is kind of an upper limit on how much mass can be ejected with an asymptotic speed of this speed. But you could get mass loss up to of order of solar mass.
And Parker wind, the two are always comparable.
The what?
And Parker wind, the two are always comparable.
In a...
Gravitational and the kinetic.
Yeah, I mean, I think that's sort of true, sort of not. I mean, there are cases where the asymptotic speed is 1/10 of the, and so I would say when the asymptotic speed is 1/10 of the escape speed, that means the vast majority of the energy has been lost into work done against gravity. Okay, so back to David's question. So if you look at different stellar models and different times in stellar evolution, you actually get a fair amount of variation of exactly when during stellar evolution and which phase of stellar evolution is the most important for unbinding material by this mechanism. And that has to do with a variety of factors. It has to do with where the energy damps in the stellar envelope, so the exact frequency of the waves. It has to do with whether or not there's actually, in some cases, for some progenitors, there isn't enough time, as Duran was alluding to, for the waves to actually propagate all the way out to the stellar envelope. And so what this shows is a plot of the onset of mass loss from our kind of best analytic order of magnitude estimates. So that's what this really is, as a function of the helium core mass, the mass of the core of the star near the end of its life. This is kind of a proxy for zero-age main sequence mass, massive stars, low mass stars. But this is better because different zero-age main sequence stars with different mass loss histories that have the same helium core mass at the end of their life will have similar properties. And so the thing to emphasize here is just that there's actually a lot of variation in when mass loss gets triggered. It varies from a few decades to a few months, with most of the dependence really being on the mass of the star. And this is basically at its core, this is a version of something you already know, which is that very massive stars go through their fuel much more quickly than low mass stars. That is actually true in late stages of stellar evolution as well as early stages of stellar evolution. And that's responsible for this kind of rough correlation.
Your time is measured backwards from supernovae?
Correct. This is time prior to core collapse. Exactly. The other thing to emphasize is that just dumping energy into the envelope prior to core collapse doesn't guarantee that you unbind the envelope. These are two examples where I dump energy into the envelope. In one case, the star expands out to become a giant. In one case, the star does absolutely nothing interesting. The difference is that in this case, this is radius as a function of time. In this case, the energy is deposited deep in the envelope where the thermal time is longer than the time until core collapse. And so you just don't have enough time to adjust the structure of the star prior to core collapse. So in this situation, the star, when it collapses, would be filled with all these waves trying to move out and change the structure of the envelope, but there wouldn't have been enough time for them to do anything. And so it's only in a fraction of progenitors where we actually think that this mechanism would work to unbind a significant amount of mass. We looked at about 100 different progenitors, mostly different masses, but also some different metallicities, things like that. And what we found is that in something like a few to 10% of progenitors, the waves were deposited at the right place, and the waves could tunnel through this propagation barrier in the envelope in order to actually unbind an appreciable amount of mass. So this, no, it's actually a range of masses. There's it's favored actually in both comparatively low mass stars, but then also there's a range of masses at 40 or 50 solar masses where it also works. And there's different reasons.
In this intermediate range where it doesn't, where it
Yeah.
crash and things go to collapse.
Yes.
Does this produce any anisotropies in the collapse?
So I don't know. I think probably the dominant anisotropies in the collapse will be generated by the convection itself. There's more energy in that than in the waves, so that's my guess. So I think this is an interesting question. This is an additional source of asymmetries, but this energy is still quite small compared to the total binding energy of the core, so I think it's not a huge perturbation to the structure. Metallicity does matter, some mostly because it changes the mapping from zero-age main sequence mass to final core mass, so it does matter. But I would say that's essentially completely degenerate with mass loss history.
What about rotation?
Rotation matters, but I don't really believe models of stellar evolution with rotation. So it does matter, and it could matter a lot in the following sense. If the rotation rate is comparable to the convective turnover frequency, you change the statistical properties of convection and the wave excitation and propagation. So I think that's a very interesting case. Everything that I've done is the non-rotating limit. So I do think the rotation is potentially quite important. That's a yet harder problem, so we haven't really looked at that. I think the typical magnetic fields in the envelopes of massive stars are not significant to affect the propagation of the wave. So I don't think that's that significant. Oh, sure. I mean, I think the magnetic field may be very important for the rotational evolution of the star. Yes?
What is your assumption for wave damping?
So the waves have small amplitudes, so they don't steepen or break or shock. And so the damping is calculated from linear theory, and it's mostly radiation diffusion. And I think that's actually a very good approximation. Even though it sounds like a lot of energy, the amplitudes are still very small. So the waves are not, I mean, that's kind of related to David's question. They're not perturbing, delta V is small compared to CX. The waves don't damp at all in the core. The neutrino damping time and the thermal time is so long that there's no significant damping in the core. They really only damp near the surface of the star. Oh no, the thermal conduction is subdominant compared to radiative diffusion. Okay, so in the last little bit, what I've been telling you about now is waves excited in the core going out. What I want to switch to in the last little bit is just briefly tell you about waves excited in the shell phases going in. And this is work that was led this past year by Jim Fuller, who's a really good postdoc at Caltech and KITP. So it's the same idea. You have phases in stellar evolution where the core is radiative, but there's a shell burning phase of carbon, oxygen, silicon, etc. Huge amounts of energy being generated by fusion, moving around by convection. Those waves are going to propagate both directions. You're going to excite waves going out, excite waves going in. I'm going to focus, because I kind of already told you what I think is the most interesting thing about the waves going out. I'm going to talk a little bit about the waves going in. And I think the most interesting thing about the waves going into the core of the star is not that they affect the thermal structure of the star, because they do, but I think that's a very small effect. But it's that they can affect the rotation of the core of the star significantly. So internal gravity waves carry angular momentum in addition to energy, provided that they're non-axisymmetric, so spherical harmonic decomposition of the waves. If m is not 0, there's an angular momentum flux associated with the waves, which depends on the energy flux and the frequency of the waves. And we think we know the energy carried by the waves, the frequency of the waves, so we think we have a sense of how much angular momentum they're carrying. So what is an interesting amount of angular momentum? So here's one way to think about it. A typical neutron star, according to what we infer observationally, is born with a rotation period of maybe 100 milliseconds. And that corresponds to an angular momentum, which is about 10 to the 47 in CGS units. 1.4 solar mass, 10 kilometers, 100 millisecond rotation period. The core of the star, prior to core collapse, what that means is if the core of the star, where the waves are propagating into, if that has an angular momentum of order less than, bigger than 10 to the 47, that's kind of the angular momentum scale we're interested in, because that's the typical angular momentum of the neutron. For black holes, I would say we know much less about what the spin periods are at birth. So if I focus for now on just one sign of the angular momentum flux, waves travel in both directions around the sphere, so they actually carry angular momentum of both signs. If I focus on just one sign of the angular momentum flux, the angular momentum carried by the waves going into the core is huge compared to what we think the angular momentum content of a typical neutron star is. So it's actually a very large effect on the angular momentum content of the resulting neutrons. So that's kind of just the order of magnitude. You know, think about the energy/angular momentum budgets in the problem. Is it important? Is it not? And it depends on exactly whether you're talking about carbon shell fusion, silicon shell fusion, but that's a detail. It's a big number no matter what. So the question is, what effect do these waves actually have on the rotation of the core of the star, given that the core might be rotating already, the shell might be rotating already, you excite waves which have both signs of angular momentum flux. And I think, honestly, that that's a hard problem, and there's a lot more to do to really understand this problem. What I want to do is give you one kind of extreme limit of what might happen. This really is just setting the stage. Ultimately, I think we have more work to do to fully understand this. Jerry? Was there?
It just goes to the lowest energy state.
Maybe. That's where do the waves get their angular momentum from? Yeah, they get it, ultimately, I would say the way to think about it is they get it from the shell, from where they're excited. It's the angular momentum here gets transferred into the waves. And then, well, the angular momentum is conserved. The collapse amplifies the rotation, exactly. So here's the one extreme possibility. Imagine that the iron core just prior to core collapse wasn't rotating at all. That magnetic fields were very efficient in the subsequent 10 million years at coupling the core to the envelope. It transfers the angular momentum out, and so as the core contracts, it spins down. And so the core is very slowly rotating. Then what we think will happen is that this wave excitation process is really a stochastic process. And you can kind of see it in this movie. There's individual convective plumes come up, generate a pulse of gravity waves that transfer energy and angular momentum into the core of the star. Then another plume comes up, transfers energy and angular momentum into the core of the star. Yeah. So correct. So what happens actually, so this part we can actually calculate. So this part we calculated, is that the waves propagate into the core and they damp by breaking. So the damping by neutrinos and diffusion is negligible in the core. It's so dense, the thermal times are so long that that's irrelevant. But the waves are geometrically focused and they get large enough amplitudes to break. So that's what we think happens. So they do actually damp and convert to the mean flow, yes. And then, I mean, as Jeremy knows, then you get all kinds of, then you start to spin up the interior of the star, which changes how the waves interact with the mean flow. You get all kinds of interesting complications that we haven't considered. So one kind of extreme limit is to think of the angular momentum content of the core of the star is really undergoing a random walk because it's being pounded by individual convective plumes carrying wave packets. Individual convective plumes launch wave packets which carry kind of a random amount of angular momentum from the shell to the core. In that picture, the core would end up with an angular momentum content which is equal to the total angular momentum dumped into waves divided by the kind of standard root n of how many random pulses have you given the core. And the interesting thing, the thing that I think was surprising about the late stages of massive stellar evolution is there's actually not that many eddy turnover times. Fusion happens so fast that there's only like 100 eddy turnover times for the convection in the kind of last bit of silicon fusion. On the main sequence, the sun near the base of the convection zone, where the turnover time is a month, it undergoes almost 1 trillion eddy turnover times. So this random walk stuff is kind of irrelevant in the sun. It's a much more secular process. But when you only have a small number of eddy turnover times, the angular momentum exchange can actually be dominated by just this random process. And this would actually correspond to an angular momentum content if the core was initially not rotating at all and then randomly gets some angular momentum from the waves. This corresponds to a typical angular momentum content of a neutron star, which is equal to that of a typical 100 millisecond pulsar. So that assumes that the angular momentum content of the core and the shell are well coupled to each other. The waves damp by breaking and deposit their angular momentum relatively deep in the core. So this picture, I would say, is relevant as long as the core and the shell, or the core and the envelope, are not very well coupled during this last phase of silicon shell fusion. Yep. Yep. Exactly. Yep. Yep. Yeah. That's right. So angular momentum is conserved. The shell has to lose this amount of angular momentum in order for this to work. That's right. So as long, I think in this, so I would disagree with that. I would say even if they're both not rotating at all, because you're undergoing this random walk, you can still have a very small but finite net exchange of angular momentum. I mean, the shell would have to, in that limit, the shell would have to rotate slowly in the opposite direction. And in this picture, the orientation of the angular momentum is completely random because it is this random walk. So we looked at this for different mass stars, and it actually turns out not to vary a lot with mass. So more massive stars have fewer eddy turnover times, but the waves have more, the convection is a bit more vigorous, and those kind of cancel out. So, yep.
You know, this different burning regime. What is the breakup function? Because it's like
Oh, it's very well. You mean due to the rotation, or due to something about the convection?
No. So you rotate.
Yeah.
But it's different in like every.
Yeah. This is still very, very slowly rotating.
But how much?
This is in the. So the number I remember is the neutron star. So in the iron core, the rotation rate is very long. So breakup is like a second. So this is 1,000 times breakup. So very. In the iron core, it's 1,000 seconds, which is very long.
So 0.1%.
Yes, that's right. So it's very, very slowly rotating compared to breakup. Okay. So, you know, I think the real take-home message here is I think that the massive stars have had tens of millions of years of evolution of their angular momentum content. And that tens of millions of years of evolution may be entirely irrelevant to actually setting the angular momentum content of neutron stars and black holes. It may be dominated by the inflow of angular momentum carried by waves in the last day or so of evolution, silicon fusion, last month or so, carbon fusion. And exactly how those waves affect the angular momentum of the resulting core will depend on whether the core was rotating before or not. If it's non-rotating, this is one limit of what can happen, which is you get this kind of stochastic process which randomly builds up a small but interesting amount of angular momentum, which is conveniently comparable to what we actually infer for the birth periods of neutron stars. Okay, so I'll end there and just kind of reiterate that I hope I convinced you that the standard story of massive stellar evolution, where the cores of massive stars are decoupled from their envelopes, is likely incorrect in at least an interesting fraction of massive stars, and that energy and angular momentum redistribution by waves, what is really a non-local redistribution of energy and angular momentum, can actually have a very large effect on the structure and properties of the star. This can explain some of the very large mass loss rates that we see associated with core collapse supernovae, and that the angular momentum carried by the waves may actually reshape the spin of the stellar core, affecting the rotation rates of neutron stars and black holes when they form. So, thanks.
We have time for a few questions.
Yes.
This is brought up by some of the questions from before. And it's on the question of what mechanism drives the wind.
Yes.
In the solar case,
Yes.
waves coming from below steepen, and magnetic fields are extremely important
Yes.
in carrying this energy and the steepening and the energy decreases.
That's right.
So this is relative to the questions that Russell and Eve asked.
Yeah.
And even though the magnetic fields in the solar case are typically quite small dynamically,
That's right.
they're very important for the energy transport
Mhm.
and energy deposition. The problem is complicated enough without that,
Yeah.
so I understand why you didn't include it. But can you just go through the thought experiment if you had included
Yeah.
the mechanism similar to what happens in the solar
So
core?
here the waves damp inside the photosphere. Okay.
By hypothesis.
No, by calculation. It's linear radiative damping of acoustic waves. I think I mean, I do think that we understand pretty well, and I think the magnetic fields are not strong enough in massive stars to affect the propagation at that location. No, I understand, but these are outgoing acoustic waves, and I don't, the field, kilogauss field even, which is a strong surface magnetic field for a massive star, is not enough to affect the propagation of these waves at all. So I think the waves they're sound waves, they damp by radiative diffusion inside the photosphere. And then the wind is basically, I mean, you can think of it as two ways. One is the optical depths are so high that the photons behave like a fluid, and so this really is a thermally driven Parker wind, but it's radiation pressure dominated rather than gas pressure dominated. The other way you can think of it is, which is basically equivalent, is that it's continuum opacity. Right? You generate this huge energy flux associated with dumping all this energy into heat, and that produces a large radiation pressure force due to continuum opacity, nothing to do with lines.
Magnetosonic waves would not carry it.
I don't, I mean, there could, I guess the question is, once the waves start to damp, do they then transition somehow in, you generate a bit of convection? Does that dump energy into magnetoacoustic waves? Maybe.
That was what I was thinking of.
Maybe.
And those propagate out.
But, I do think the problem is different. In the sun, it's all about transferring energy way outside the photosphere. Here, you're dumping enough energy in to simply unbind the envelope, the entire envelope at the place where you deposit the energy. So I think it's very hard not to get a wind in that case. And I do think it really is sufficiently high optical depths that it's fluid-like. So what I would say is that where this gets more challenging theoretically, and I think becomes much more like the solar problem, is as you go to, say, carbon fusion, where you still actually get an interesting amount of energy coming in waves, but it's like 10 to minus 2 of the photon luminosity of the star. There, it really matters where the waves damp. If they damp inside the photosphere, a 1% change to the photon luminosity is not very important. If they damp outside the photosphere, it has a really big effect. So I think in the earlier stages where the waves are carrying less energy and it has a less dramatic effect on the structure, then I think it really does matter where they damp. And you know, I've looked at this a little bit, and as far as I can tell, the waves still damp deep in and probably don't do anything interesting. But I think that problem is much more analogous to the solar problem.
My question has to do with the convection in the core.
Yep.
And the properties of this convection will be somewhat different than most other convective regions in stellar interiors, in that it's still strongly dominated by neutrino cooling.
Yes.
So it's not adiabatic. So the fluid element perturbations are not adiabatic. They can cool.
Yes.
And so it's not clear that the convective velocities would be similar because one fluid element
That's right.
cooling. So is it okay still to apply
So-
the scalings from the
So I guess I would say we compared the analytic mixing length theory type estimates to the multidimensional simulations with neutrino cooling that Casey Meakin and Sean Couch have done, and they agree actually reasonably well. The convective velocities are a few times higher in the simulations compared to mixing length theory, but they're reasonably consistent. And I think it's because, I mean, it's true the fluid elements become non-adiabatic where neutrino cooling is important, but the temperature fluctuations are still really small. It's still very efficient convection in the language of stellar structure. So the entropy fluctuations are small, the density fluctuations are small, the temperature fluctuations are small. And that's because the amount of energy you're moving around is huge compared to Eddington, but it's very small compared to rho CS cubed. And so you don't need much buoyancy, you don't need much density fluctuations. And I think that's why the mixing length theory is okay. I mean, I think that's why it's still okay. I mean, you have to take into account the specific heat of this matter, the compressibility. So it's not literally the same mixing length theory that's used in the sun. It's a mixing length theory that's appropriate for the thermodynamic conditions in the cores of massive stars. Yeah. In the very core. Yeah. Yeah. Yes. Yeah. Yes. So it's actually a fun calculation. So if you have a wind that has a super Eddington kinetic power, you also end up with a super Eddington photon luminosity. This is what Jeremy is alluding to. It's not quite as large as I was hoping. So it becomes so the photon luminosity of the wind, L photon, sorry. So the photon luminosity of the wind is bigger than the Eddington luminosity by the ratio of the kinetic power, that's this Ln, the kinetic power in the wind to the Eddington luminosity. And this is actually consistent. The one-dimensional MESA calculations that I did have radiative diffusion, so it's kind of like it's a not great version of flux-limited diffusion radiative transfer. So you can, and what you find there is the wind luminosity is kind of order this. Now, what happens actually, this I would say is not enough of an increase above Eddington to be interesting compared to what's observed in those pre-supernova outbursts. Just the 1/3 scaling is kind of weak. What happens in the calculations that I've done is that when you dump energy into the stellar envelope, initially you're dumping energy into a lot of mass. And so initially, the stellar envelope moves out quite slowly. As time goes on, you're evacuating the stellar envelope, so you're dumping the energy into less and less mass at the location where the heating happens. So as time goes on, the wind accelerates to higher speeds, and you get basically an internal shock. And so what I think actually happens, at least in these toy models, is that a lot of the kinetic power gets converted back into photon power at large distances by a shock. And that may actually be more important than just the advecting out of the photon luminosity, which is what this is.
Okay. So thank you very much.